morning's physics fight. First of all, I would like to introduce 5 juries, and I will chair this fight. My name is Xiangming Lu. I'm a physics professor at National Taiwan Normal University. And our second jury is Professor Lian Zhenxun from National Central University. So please give a hand. And the third jury is Professor Wen Buguo from National Zhongzhen University. And the fourth jury is Professor Yang Jiahui from Hongjia University. And the fifth jury is Professor Li Jingrong from National Zhongzhen University. Next, I would like to ask the reporter UCN 1917, the captain, please introduce your members.
And hello everyone, we are Team ECN 1917, and I'm Zheng Zixing, Hu Yulin, Anhui Li Zhanglin, and Chen Yuli.
And our opponent, ex-trivials, the captain. Okay, captain, please introduce your team members.
Hello everyone, we are Team Trivial. We are from Jiayi Junior High School, and my name is Fang Haoyu, and this is Xiao Yucheng, and Zhu Rongxuan, and Huang Qirui, and He Chengyong. Thank you.
Okay, welcome. And the reviewer, LATY, the captain, please introduce your.
Hi everyone, we are ATY, and my name is Ding Jun, and this one is Li Zhouting, Chen Hongping, and Li Yahui.
Okay, thank you very much. So I'm very glad to see many female students here to join this physics fight. Okay, so we will start the first one. The opponent challenged the reporter for the problem.
But we would like to challenge problem 9.
Problem number 9. So, reporter, you have 1 minute to decide accepting or rejecting the challenge. Problem number 9. Okay, the reporter accepts the challenge of problem number 9. Okay, so please write down your represented for each team. And now we go to the preparation of the reporter. 5 minutes. Ask the ladies. So opponent, so could you write down the name of the representative? Yes.
Can I take off my mask I'm recording?
Uh,
Would you mind that?
Jury is okay. Okay. So you can remove your mask during your presentation.
现在划到光电系去了，对，对。以前是有物理中心，对，那就因为光电系以前是物理中心出来的，但后来因为物理中心学校都要整了，其实就把物理中心变成光电系去。
Okay, the Ruin will give a presentation, 12 minutes. Please.
Hello everyone, my name is Chen from Team ECN 1917. The topic I'm going to talk about is number 9, oscillating screw. So here's our problem statement. When placed on its side on a ring and released, a screw may experience growing oscillation as it travels down the ring. Investigate how the motion of the screw as well as the growth of these oscillations depend on the relevant parameters. So we'll mainly focus on the motion of the screw and the phenomenon under various parameters. So here's the video. So you can see that we place the screw with a certain angle and release it. You can see that while sliding down the ring, the screw will oscillate and have a growing oscillations. And we will define that later. So here, we need to know the structure of the screw first. So this part is the head of the screw, and this is the mass. So how do we know the mass of the screw? We use the torque of it to analyze it, use the rope to know that, oh, this part will be the mass. So as for the tail, it will be counted from the end, and this third thread will be the tail. And for the imaginary graph, this one is the axis, go through every circle of the center, and this one is the tail, this one will be the head. And we will later on use this one to analyze the angular velocity. And here is our observation. So we found out that in our experiments, this is the ring, the phi is the angle of the ring, and theta is also the ring. And you can see that the theta is bigger than phi. So when these 3 points, these 3-point dots, is almost a horizontal line, it is hard to sliding down. It is because of the component force of the weight of the screw is not enough. But when this part, it is bigger than that, it will have a component force of that to let the screw slide down. So we place this on with our experiment. So we found out that when this part, when these 3 points form a line, which is not a horizontal line, it is very easy to slide it down. However, when it is almost the horizontal line, it will pause for a second and then sliding down. So here another point for our horizontal line for this is the structure of the screw. So if the radius of the head is bigger, and then these 3 points will hard to form a horizontal line, which means that it will not be easy to sliding down, which means that it will have an oscillation of it and pause for a second. As for the other part, this one will be easy to sliding down. So here, later on we will use energy analysis, sliding analysis, oscillating analysis, and torque analysis to talk about our phenomena. So here's the energy part. This one is gravitational potential energy, and it will equals to the sliding kinetic energy plus the oscillating kinetic energy plus the friction loss of the kinetic friction, the sliding down kinetic friction. And here is we'll move on to our sliding analysis. So here we can see all the forms of it with the diagram, and here we will capture a moment that the phenomenon appeared. So this is the first moment. When the screw is at this side, the factor that will influence the sliding will be the weight of the component force, and we have to minus the kinetic friction force, which avoid the screw to sliding down, and plus the kinetic oscillation friction force that affects the sliding force, which one this arrow will be sliding down. So this part will be the force that increase the sliding force. However, when we move on to another second, when the screw sliding to this part, the oscillation kinetic friction force will go up to the left side, and you can see that the part right here, the arrow will go up to the opposite direction of the sliding direction, so it will become minus right here. So in this moment, the sliding force will be smaller than this moment. And that's what caused the fluctuation of the acceleration, because the force is different, and then the acceleration will be different. So here is the graph that we found analysis about our phenomenon. So we found out the graph of that. You can see that the fluctuation of the acceleration, it is because that the force analysis that I just talked about. And why the acceleration will increase by time? It is because of the inertia. Because the inertia, what is inertia? Inertia is like if there is no any force due on the screw will keep the motion of it like original motion. However, if there is an oscillating kinetic friction force, it will add to that screw and then got a new force and then add the acceleration. So that the acceleration will increase by time. So the problem statement asks us to see the growth oscillation. So it's because of the new force of oscillation kinetic friction force, then the amplitude of oscillation amplitude will be increased by time. So we took a part of the graph and then get analysis. And we also think that the fluctuation of the screw is also because of the self-rotating of the screw. So next, we'll move on to our oscillation analysis. So we use the torque to analyze why the screw will rotate. So you can see that our observer is at ground and the other one is at center mass. So for the torque, we were trying to use the center mass of the pinch for the point, because that if our observer is at ground, it is hard to know that which point because the screw was sliding down. So it will move all of the time. So we're trying to use the mass to calculate the torque. And later on, we will talk about our angular acceleration, because angular acceleration will also hard to calculate because of the move, because of the screw is always moving. So we will also use this one, the coordinate system of it, to calculate how the screw will rotate and how should we know about our angular acceleration to do analysis of it. So here we will use angular velocity part to describe again why the screw will oscillate and why they will have the growth of oscillations. So here we all know that there are 3 different kinds of angles. The first one is alpha, and then this is phi. The alpha is the ramp inclination, and alpha is the oscillate amplitude, and the theta depends on the structure of the screw. So what caused the oscillation? This is because that in the same system, the screw, the head and tail, angular velocity of it will be the same. So their radius of that, their oscillator radius will be different. When the big R is bigger than the small r, and the angular velocity should be the same, and that the velocity of head and the tail should be, the head of the velocity should be bigger than the tail, so that this part will go faster than the tail, and then cause the oscillation. And what caused the growth of the oscillation? It is also because of the new force, oscillation kinetic friction force. And then they will have the acceleration, and so the velocity will increase, and then this part will also increase. Then, according to the formula, the oscillation amplitude will also increase, then cause the growth of oscillation. So the growth of oscillation right here, we both use the coordinates of the screw to analyze with Python and know that how the oscillation will increase. So next we'll move on to our experiment setup. So we use foam, acrylic sheet, screw right here, and 3-prong clamp and ring stand to do our experiment. So this part, the foam should be parallel to the ring, make sure our experiment is accurate. And here is our first parameter, the ring inclination. So we found out that when the ring inclination increases, the sliding velocity will increase. And why does the velocity will increase? It is also because of the sliding acceleration that we just talked about. And why it will have some fluctuation of the velocity? It is because of the fluctuation of acceleration. It will also have a fluctuation. And next, we will move on to our oscillation amplitude. So we found out that when the ring inclination increases, the oscillation amplitude will decrease. So we were trying to use the energy analysis to talk about this part. So we found out that the ring inclination increased, which means that the gravitational potential energy will increase, and because the angle increased, the sliding force will also increase. Then the sliding kinetic friction force will also increase. However, the increased amplitude of that, the sliding kinetic friction force will be bigger than oscillating kinetic friction force. Because in the phenomena, we found out that, please look at the blue part. Like, they have the highest angle. However, in the phenomena, we found out that the velocity of it will be bigger. So the sliding motion of the screw will be, more appearance than the oscillating. So we think that is why the ring inclination increase, the oscillation amplitude will decrease. Next one, we'll move on to our screw length. So this one, when the screw length decrease, the sliding velocity will increase. So we all know that when the screw length decrease, the normal force of it will decrease, and then the kinetic friction force will decrease, then the sliding force will increase, so that the sliding acceleration will increase. And also for the fluctuation, it is also because of the acceleration. And here for this part, same. We would like to use the energy analysis to talk about it. So when the screw length decrease, the oscillation amplitude will be increased. So we also use the energy part to analysis. The gravitational potential energy increase, the sliding force increase. Then this part, the sliding kinetic friction force, sliding kinetic energy will bigger than oscillating one. So that when the screw length is shorter, the oscillation amplitude will be more apparent to see that in our phenomenon. So here is our conclusion. The oscillation kinetic friction force is the reason that causes the screw to oscillate, and the component force of it affects the sliding motion, the fluctuation of velocity and acceleration. And the other one is the inertia plus oscillation kinetic friction force cause the growth of oscillation, and when the ring inclination is bigger, the velocity is faster, but the oscillation amplitude is smaller. When the screw length is longer, the velocity is slower, and the oscillation amplitude will be smaller. And thank you for your attention.
Okay, thank you. So we move to the next phase, the question of the opponent to the reporter and answered by the reporter. So opponent, you have 2 minutes.
The first one, please turn to page 10.
Page 10. Okay.
You mentioned friction force in your presentation. I would if the friction force is spin friction or if it's just a slight friction.
Oh, for this part, this friction will be the oscillator friction. So sliding friction and the oscillation friction is different kinds of axes, so it will not affect each other. So what cause the oscillation, for my opinion, it will be the oscillation kind of friction.
Okay, thank you. So we go to the next phase, preparation of the opponent, 3 minutes. Okay, now the opponent will take the floor, maximum 4 minutes, please.
Our team serve as the opponents of this round, and we are going to oppose question 9, oscillating screw. And we are team tribute. The problem statement is that when placed on its side on the ramp and released, a screw may experience growing oscillations as it travels down the ramp. Investigate how the motion of the screw as well as the growth of these oscillations depend on the relevant parameters. And some of our key points include how to construct a stable environment to test out experiments, what is the theory behind the increasing oscillations, and how do different control variables affect the outcome? This is the overview. First, the phenomenon is that the screw may experience growing oscillations as it travels down the rack. And the theory is that horizontal line energy analysis, sliding analysis, oscillating analysis, and some experience are screw length and ramp inclination. These are some advantages and suggestions. Advantages include this: you have great time management, clear explaining of the phenomenon and lots of pictures, successfully created phenomenon, qualitative explanation of the phenomenon, and persuasive theory. Suggestions that you don't have enough experience data. Maybe you can do more experiments to further prove your theory. And points to be discussed.
So now we move to the discussion.
The first question I would like to ask is that how will the size of the screw affect the phenomenon, like the actual frequency of the oscillation?
So you mean the size of the screw is kind of like
The length.
the length. So can I draw the blackboard? So for the length of the, so for the horizontal line, this part is the screw, the length of it, the ratio of the screw. So this one will be, this one will be the length of it. So here, this one, when the screw is longer, this part you will see that this is more easier to form a horizontal line. So from our discovery, we found out that when the screw structure is like this, it is hard to have the oscillation rotate. It is hard to sliding down. It is hard to sliding down since in this part, when the screw is almost have a like a horizontal line, just like like in my slide, this moment will be like this one for the pulse. So it was hard to be sliding down. But when the screw, this line, the structure of it, the head, the center of the head, and the mass, and for the tail, this part will not be a horizontal line. So it will be kind of like the motion like this. So like this. It is easy to slide it down. And as for the other one, the size of the screw, we also found out that the tail shape will also influence it. Because some kinds of screw, it will have some irregular shape in the tail. So if we want to see the problem statement talk about the oscillation of the screw, you have to pick the screw, because some screws have some like a triangle shape in the tail. So the triangle shape will make it hard to rotate. So yes, I do think the size of the screw and the structure of the screw will affect our experiments.
And how will they affect the frequency? Like if I shorten the length by half, will the oscillation frequency get turned by half?
Oh, you mean the period?
Yes.
So as for the period, the shorter one will have more period in same length. For our length, we use the 91.7 centimeters. So for the shorter one, the period of it will appear more times. Like in a short time, every time they're sliding down, probably for the 5 seconds, and their oscillation period, this one will appear more, and this one probably just for one time, just for once. So for the longer one, it will be shorter, and for the shorter one, it will be more oscillation in the 5 seconds.
Okay, the next question. Will the screw thread affect the experiment, and how will it affect it?
So for the theoretical part, we all know that theoretically, there was no analysis for the thread, because the thread of it just depends on some company that they will make their screw, the shape of it. So for the theoretical part, I don't think the thread will affect our analysis, but for the reality, I think that it will affect a lot. Since I just talked about the thread of it, they will have some triangle shape, and it will make the phenomenon that oscillates hard to see. So yeah, that's my answer.
And my suggestion to this question is that maybe you can move the thread of the screw down. Maybe
You mean like shave it, like
Yeah.
cut it, use some machine?
shave it and make the sides more smooth.
But I think it's hard because because we have to think about that, but the screw is round shape, and we cannot, you know that the thread of it is not like just a circle and a circle and a circle. It will be like this one, just like a typhoon, the shape of like a curly hair, like this. So if you use the machine to shave it, like to more smoothly, not have the triangle part, it is still hard to observe it, and you cannot be sure if the shape surface of it is smooth or not.
Yeah. So if you didn't smooth the side down, then did you take the thread carefully? Like, did you measure it before you did the experiment? Like the thread is better if the teeth are the same distance.
So yeah, for the proper statement, we have choose a lot of like all kinds of screw, but the proper statement asks us that we need to find the phenomenon of oscillation and growth oscillation. So when we are trying to do the experiments, we want to do for the experiment data, we find the screw that with this shape will be our best choice to fit with our problem statement that it will oscillate while sliding.
To experiment. How do you make your measurements more precise?
Like
Do you
for
use tracking apps?
like tracker, yes. And first of all, that our experience setup. For our experience setup, the phone, if just assume this one is the ring of the sliding ring. Yes, this part. So the ring of it, we have some square of it. So the phone have the camera in the phone have the square. We can like set up our phone, the square in our camera that we can match with these squares, so that the phone, we want it to parallel to the ring. And with the square in the camera, we can know that, oh yeah, it is exactly the parallel part. So from the shooting video, it should be accurate right here, I think. And for the angle part, the ring inclination we will not use something to measure the angle right here. We trying to use, you can see that in my data, 27.6 degree. The degree is very weird because the way that we do our ring inclination is we use the 3-prong clamp to higher the ring and calculate the sine. I don't know how to say it, but we use the Excel to calculate this one. To use the sine and cosine tangent to calculate the angle of it. So the angle is weird, the data, to make sure. Yeah.
And another question is that how do you make sure that the slide is flat enough?
slide.
Yes, it might have bumps and dents in it, but you have to make sure it's flat enough for the experiments to be more precise.
Because we have calculated the torque of the, you mean like the ring, you mean the screw may like bump, like will jump, which means that the ring is not smooth, right? So we did calculate the torque of it, so we found out that when when we set the screw head of the mass of the screw right here, the circle of it is the pit, right? Yeah, and this is the force of it, and here it will be the kinetic sliding friction force, and we try to calculate the torque of it, and we found out that the screw will not jump because it will also have a normal force of it, and then the friction oscillation force of it, and then when we're trying to use the torque to calculate it, we found out that it will not jump at all. It will be the amount of it will be just like 7.389 for the head, and as for the tail, it will be, so their difference is just very small. So for oscillation, the phenomena of it, we don't think that the jumping, like the ring smoothly or not, will affect our experiment. And as for those acrylic sheet, the coefficient of kinetic friction, we calculated is about like 0.508, and we also use the sandpaper to test it if it can sliding down or not. But however, the sandpaper is the coefficient of it is too big. It's about like 0.8. So the ring is smooth or not, we have calculated. Yeah.
My last question is that how does the Python script help?
So the Python, we would like to use Python is because that the screw will moving. So the screw right here, we were trying to use the coordinate of it. Like we will put it into the Python to know that the first one, what is the angle of the screw? This is the timing will be a 0, this timing will be a 1, and this will be the second part. So first of all, we use Python to know this angle, and then
Sorry, so
know
have
the
to
angular acceleration.
the opponent summarize the discussion.
The summary of this discussion is that I asked the reporter will the size of the screw affect the phenomena, and she answered yes. The size or the length more precisely it will affect the period of the oscillations. And next, will the screw thread affect the experiment? And the reporter answered yes. And how to make your measurement more precise? And they answered that they use tracking apps such as tracking. And how do you make sure that the slide is flat enough? And they tested out with sandpaper and screws and found out that the differences is too small. And
Sorry, so now going move to the question of the reviewer, to the reporter and the opponent.
I'm reviewer, and I want to ask the reporter that you use that the board by 91.7 centimeters, right? And if you use the board longer than that, you see the frequency is will like be using 1 second, or 1 will 4 to 5 times.
If I use like for about like 3 meters, I think that the shorter screw will still have the more period that we can observe, because the screw is the longer screw was hard to have an oscillation.
Yeah, but the frequency will the same.
So you mean the frequency? So the frequency will kind of like this. So if we already know the period of it, so I think it will still have the result like I just talked about when we use 91.7.
But if for a long time it will big, and the frequency will don't affect that.
The frequency, you mean the frequency will affect the oscillation growth?
Yeah,
the
or
growth of oscillation.
Oscillation will affect the frequency.
The oscillation will affect the frequency. No, because when you're sliding down, the velocity of it is also sliding down. So the way that the screw rotate will also be faster, even though they have the growth oscillation.
Yeah, what do you think about that?
I think that maybe they can use more length of the screws and make more measurements so that they come up with a more accurate.
Okay, and I want to know how do you put the screw down if you put or you push it?
No, we would like to place it on the ring, which means that the velocity of it is zero, it is stalled, and then release it with a certain angle. And with the angle we use is the 45 angle, so 45 degree. Yes.
But how do you measure every time you put it down in 45?
Because this paper is a kind of special paper. This one is a graph paper, so they have a little square in this part, so we know that we can measure it.
Thank you. So, preparation of the reviewer, 2 minutes.
Hi everyone, it was in
Preparation. 2 minutes.
sorry.
Okay, now the reviewer takes the floor.
Hello everyone, and today we are going to go that observatory screen. And the topic is when placed on a side on the roof and realized a screen may be experienced screen observation as it rolls down the roof. Investigate how the motion of the screen as well as the growth of the oxygen depend on the relevant component. The main focus, the motion plus the support, the phenomena of the various components. In conclusion, the rotating ring connection is bigger, the velocity is faster. Acceleration diffraction force is the reason that causes the fluid to oscillate. Discussion 1. Opponent asks the reporter if pressure for slide friction or reporter said the cause of the ocean is the ocean friction. And discuss to opponents as the reporter said, will the size of the screw affect the phenomena? The reporter said for the person line it is hard to find that the tail shape will also influence the oscillations. And this opponent and reporter if shorten the length by half, and reporter said the period of it will appear more time. And discussion for opponent asked reporter said will the screw do affect the experiment. Reporter said they have 3 kinds of screws to fit with the problem statement. And discuss opponent asked reporter how to measurement more precise, and reporter said use the way they calculate the ratio to calculate it. And that's I asked the reporter say if you use the longer board to experiment and will affect the frequency, and she said it will not be affect frequency. And the and the rotating square is won't affect that also. And the opponent say it thinks so too.
Okay, thank you. Now, the concluding remarks by the reporter.
Thank you for your advices for the opponent and the reviewer. So here I'm going to talk about my remark. So first of all, for the explanation of the phenomenon, so I do analysis for the energy analysis part for the opponent, and the sliding analysis, oscillating analysis, and angular velocity analysis. And as for the experiment data, you say that it is not enough. So yes, I have done more than three kinds of screw. The length of it, I've done the five kinds of length. However, I think that maybe perhaps the length of it doesn't have much change, so that the graph of it didn't appear much different. So I choose the more comparable length to make the graph. Yeah, but it still affects the length of it. And as for how I calculate the angle, so this one, I'm so sorry. This one is arc sine. So yeah, this is how I calculate the angle of the ring inclination. And as for the screw thread, the answer of that for me, but theoretically, when we're doing analysis, the screw thread will not affect our analysis. But for the reality, it will affect our phenomenon. So let's move on to my remark. So for my report, through torque analysis, force diagram, and energy analysis, the specialty of this topic is the oscillation of screw. And it is very different from just straightly sliding down to the ground. It oscillates because of a friction. So in here, friction is no more a force to interrupt sliding. Instead, it is the force that causes the screw to have new motion, oscillation. And then with the help of inertia, the screw have a growth oscillation in all. The oscillation kinetic friction force and inertia is why causing the screw to revolve and have a growth oscillation. And thank you for your attention.
Okay, thank you very much. Now, the questions raised by the jury. Professor Ian.
Although mechanical energy is barely mentioned in the presentation and discussion, however, I wonder if any feeling in your mind about how much of kinetic energy has been changed during this process, starting from the report.
So when the screw is placed when it is stalled at first, and then when it's sliding down, for my opinion, the oscillation kinetic energy will have more first, like a more portion of the energy transformation. However, when the screw is sliding down, the sliding kinetic energy will become more. Like the sliding motion will be more apparently. So this is, I think.
How about the change from the very beginning to the end? Yeah, the total change of mechanical energy.
Mechanical energy. So, for my opinion,
By the way, did you the mechanical energy in your physics course already or not?
no.
Oh, okay, sorry. I read.
I didn't go this experiment before, but I agree with her point and yeah.
Okay, thank you.
Opponents? What do you think?
I think as the screw slides down, the potential energy is transferred to the kinetic energy and heat loss due to friction.
So in the end, the change will be negative or positive?
Negative.
Thank you.
Okay, Professor Lee.
I'm curious about the trajectory of the center mass of the screw when it travels down the ramp. And according to your experiment, it seems to go curve.
Yes.
Why should not be a straight line?
Yes, and I think that this is because of the first of all, when the screw is placed on the highest part of the ring. First of all, the reason that will cause it to oscillate is because of the static friction and because of the x-axis friction. And then that's why it causes it to oscillate. And because of the structure, the screw structure is circle, like kind of like a circle, but not like a curly shape. So that I think this is also a reason that will cause it to rotate, like self-rotate and have the oscillation.
I think because it has more circles, so it will rotate here and here, so it will go like here, so it will not be straight. I agree with the reviewer.
Any questions from the jury? Reporter, could you show us your video once again?
Okay.
In addition to the oscillation period, how about the oscillation amplitude?
Amplitude. Oh, period. Yeah. Amplitude will be.
What effect will have influence the oscillation amplitude?
Like oscillation kinetic friction force. And because of the inertia, we think that the inertia means that it will move the original motion. It will keep the original motion. However, when there is a force add to it, which means that the oscillation kinetic friction force, it will have a new force to push it, and then the screw of it push it, and then pause for a second, like that rough, and then push it. It will be much longer because at first, because of the inertia, the screw will, if there is no oscillation kinetic friction force, the screw will just rotate with no growth oscillation. However, there is an oscillation kinetic friction force, so the force of it will push it to rotate. Then it will have the growth oscillations.
Thank you.
Sorry, can you repeat?
Oscillation amplitude. What's your opinion about this oscillation amplitude in your experience? Amplitude.
Yeah. I think it.
Okay. The opponent, do you have any suggestion of what the key factor to affect the oscillation amplitude?
As the reporter says, the oscillation amplitude gets bigger due to faster speed.
Okay, thank you. Thank you. Please have a seat. And now that a jury makes ready. Okay. And then the first one is for the reporter. Okay. 6, 8, 7, 7, 8. Okay, next is for the opponent. 5, 6, 4, 5, 6. The next one is for the reviewer. 5, 6, 4, 5, 6. Okay, so we will close the stage 1 and take a 10 minutes break. Okay. The reporter, so the opponent, okay, LATY challenge the reporter for the problem.
I want to try number 15.
Number 15. The reporter have 1 minute to accept or reject the challenge. Problem number 15. What's the problem? Adapter.
Yeah. The adapter is not working because we already transferred our screen to their screen, but it didn't. Seems to be like that.
Okay. Technician help.
I'll try number 15.
Accept. Okay, accept. Problem number 15. Pancake rotation. So each team please write down the representative name on the blackboard. Now we move to the preparation of the recorder. 5 minutes. Okay, the reporter will give a presentation.
So, hello everyone, we are Team Typt, and I'm going to present problem 15, pancake rotation. So, the problem statement is as follows. Place the blue balls in a round container. If you move the container around the vertical axis, the balls can move directionally with the movement of the container, or they can move in the opposite direction. Explain this first. Explain this phenomenon and investigate how the direction of movement depends on relevant curve. This is a quick overview of my presentation. So next, we move on to our experimental setup. And this is my experimental setup. There is the rotating device, which rotates the ball in particular angular velocity, and the power supply to supply the powers, and then the camera and the light source. And this is the detail of our rotating device. At the top of it is the plate, which contains the ball, and then the motor, and the knob to regulate the angular velocity, and finally the switch. Okay, so this is the phenomenon we reported. And first of all is the counter rotation. And as you can see, the balls will move at the opposite direction of the plate. and then the transition, which the ball doesn't move a lot during the rotate. And that's the rotation, which the ball rotates at the same direction of the plate. And this is our measurement methods. We use tracker to track the movement of the ball. Also, we calculate the angular velocity of each scale on or knob to get the velocity of the ball. And this is our data and the calculation. So we track the movement of the ball, and basically we set the origin at the center of the plate in order to get the position of the ball relative to the plate, also to get the angular velocity of the ball. And this is what we get as one of the results. Next is our theoretical model. So there are some patterns we observe. The cluster motion. And so first, when pushed, the space of the ball cluster will appear at the same direction as the plate's moving direction. And second, the space of the ball cluster rotates in the same direction as the plate. And this is a slow motion video that represents it. Next is the pattern is the balls will fill in the space by the opposite direction of the plate's rotation. And I want to draw your attention to the blue ball. Okay. So from the above mentioned pattern of motion, we can now analyze the rotations. And so first of all, the red line represents the boundary of the cluster. And then the blue balls are the ones we are focusing on. Okay, so first, when we rotate the plate clockwise, we expect the balls to fill in the space anti-clockwise. Okay. However, the space also moves co-directionally with the plate. So the blue balls will soon reach the end of the space and be stuck in the cluster. And we expect it to not move during the rotation when it's in the cluster. However, when the space turns around to the ball, it will move again up in the opposite direction of the plate. Okay, so compared to the first one, it rotates. Okay, so by drawing out the track of the balls, we can observe a regular pattern like this. Okay, so we expect it to be like a polygon with some, its side has some curve. However, this is what we got actually. So as you can see, there's the green line which we expected. However, there's an additional rotation, which we explain it as the slide of the ball. Okay, so the slide occurs when it's in the cluster and when it's not moving. And you noted that this slide is rather important because as the slide enlarges or decreases, it will dramatically affect the ball's track. And so this is a represent of the slide. Please look at the green blue ball. Okay, so what we do is we draw out the track of counter rotation, and so there's the slide you see we explained. And as the slide goes bigger, the ball will turn from counter rotation to transition. Sorry. Okay, so it doesn't move a lot, like it starts from here and to the end. And as the slide gets bigger, the ball actually goes from counter rotation to rotation. Like when it starts here, and the slide is bigger than the the motion we expect, so it will rotate. So we come to our initial assumption as the slide gets longer, the track of the ball changes from counter rotation to rotation. Okay, so and next is our experiment. These are our key parameters, respectively the numbers of rotating balls, the angular velocity of the plate, and the diameter of the balls. And we expect to discover their relationship between the rotation of the ball. So this is the parameter symbols we use. First, the n, the number of the balls, and r, the diameter of the ball. Omega, the rotating speed of the plate, and CTR are each for counter rotation position. Okay, so our first parameter was the numbers of the rotating balls. So as you can see in the chart, we see that as the number of the ball increases, and at the same angular velocity, at the same angular velocity of the plate, the balls will actually go from rotation to counter rotation. Okay, so our second parameter was the angular velocity of the plate, and we found out that as the rotating speed of the plate decreases, the balls are more likely to counter rotate. And finally, the diameter of the balls. So there's a problem of this because the balls with different diameter has its maximum capacity. For example, when the diameter of the ball is 8 millimeter, the plate can contain the maximum amount of ball is 70. And another example is when the diameter is 10 millimeter, the capacity was 60. So what we use is a kind of convergence of the data using the coverage of the ball. And basically we just divide the area of the ball divided by the plate, the area of the plate. And in our case, the plate was 8,100 pi square millimeter. Okay, so this is what we found out. We found that the coverage of the ball, which is we set as 0.5, don't necessarily correspond to the rotation pattern. Like when the diameter was 8 millimeter, it's counter rotate, and 12 was transition. So we come to as a conclusion that it doesn't really correspond to the rotation pattern. So for our conclusion, we tested a few parameters related to the motion of the balls, including numbers of rotating balls, angular velocity of the plate, and the diameter of the balls. And we found out that there are positive correlation and also negative correlation. However, there's also no direct correlation too. So thank you for listening. This is my presentation.
Okay, thank you very much.
And can I?
Sure, you still have time.
Okay. So this is what we did as a simplified model, but we're not sure about the relationship of them between the cluster because the cluster has more chaos. So what we did was we used the 3 gaskets to rotate. And also you can see that there is the counter rotation. Okay, so we used it as a simplified model. And so there's 3 gaskets, and we painted it as blue, yellow, and red. And our assumption was we simplified the circular motion to 4-way linear motion, which is top, bottom, right, and left. And okay, so we also assume that the friction between the balls and the plate surface are negligible. And so first, as we push the plate down, the ball will go up because of their inertia. And there's some force between the balls and the walls. And as we push the plate right, I want to draw attention to the blue gaskets, and there's additional friction of it that prevents it from moving as much as the yellow and red gaskets. So as for the yellow one and red one, and also goes to the blue one. And compared to the first image, the ball will actually counter-rotate too. So this is what we do as a simplified model. Okay, so this is the end of our presentation.
Okay, thank you very much. Now the questions of the opponent to the reporter.
Okay, so can you just turn to page 17?
I'm just wondering like what's the unit of it?
The unit of what?
Of like the x-axis and
Okay, so it's millimeter.
then from like can you just turn to like page 13? Like 14. Like you just show the space like up there, like what's the meaning of it? Does it mean like their volume is the same? Or like when they're like rotating? Like what's the meaning of it like when you show like the volume?
You mean the space of it? Okay, so the ball actually counter-rotates because they are filling in the space as we discussed on the third pattern here. So the ball filling the space by the opposite direction. So we discussed about the filling in space of the balls, but the balls will soon stop filling in because the space will move, and so the ball will stop. So we are discussing about it.
Okay, like, can you just like explain me more about like page 12?
Yes. Okay. Know about your question.
Like page 12. Like, can you just explain me more?
Okay, sorry.
Okay.
So now we move to the preparation of the opponent. 3 minutes. now the opponent will take the floor.
Okay, so my name is Mia Lin, and our team is APY, and today I'm going to host pancake rotation. For the problem statement, they place a few balls in a round container, and like if you move the container around vertical axis, the ball can move co-directly with the movement of the container, or it can just move in the opposite direction. And just kind of like explain this phenomenon and investigate how the direction shifts. And for their main focus, they focus on the number of the rotating balls and the angular velocity of plates and the diameter of the balls. And for their setup, they use like the light source, camera, and power supplies. And for their analysis, like they track the movements and theoretical model, cluster, and track. And like for the conclusion, they think that these three conclusions actually matters their ball rotations and stuff. Yeah. And I think for their pros is like they draw some picture to show that how their experiment works. And for the cons, I think like they can probably like do some experiments more to like make like kind of like a data or something, or just like a chart to show like the results. And also, I think that in some pages they put the program analysis. I think they can just like maybe just don't put the program analysis on the program. And also, I think that maybe they can just discuss about more. Maybe just like, do experience on it, and like not just like discuss about the phenomenon. Like for their friction and stuff, I think they can like kind of like make a result and make a chart of it. It kind of like shows like the error bars and stuff. So like maybe we can know more about it. Yeah, I think that's about it.
So we move the discussion.
So like can you just like turn to like your formula part? The formula?
You mean the last pages?
Alright. Oh wait, like the formula in the beginning.
Where do I? You mean this? What's the formula?
Like, do you have like formulas that talking about like the rotation stuff? I think.
Could you show your PowerPoint file on the screen?
Oh, we'll have to like set through every page. And so just that way so.
You should like scroll down, scroll up, like scroll up.
Okay, so it's okay.
Okay.
Maybe we can just skip.
Yeah. Like, do you think like there's like other like variations that will matter to the location, like other than the thing they say in your conclusion?
Okay, so I think that maybe the containers coefficient of friction may also affect the location of balls.
Do you mean like the materials? Or
Yeah, the
something?
materials
Okay.
difference.
Like, so like, can you just guess like if you're today like you're using like a glass one and like kind of like the other one that have like the bigger friction, then like what do you think will happen?
So we're assuming that the slide of the ball friction is responsible for the slide of the ball. So as the friction of the container increases, the slide may get shorter. So the balls may incline to be counter rotation rather than.
Then I was just wondering why do you choose to put your origin in the middle?
Oh, so there are two reasons about it. Okay, so as I said on the presentation, we set the origin at the center of the plate because we wanted to know. So think of it, if you set the origin on for example, on the table, then we may not know the relative position of the ball to the plate.
Yeah.
You know what I mean? Okay, so, and also we wanted to get the angular velocity of the ball. So when we set it at the center, the ball may rotate like this. So it may rotate like this, and so we can get the angular velocity of it when it's rotating.
Then can you just turn the page that when you have put your experiment video one? I hope that in the video, it kind of turns the other ways. It usually turns clockwise, right? But in one of them, it turns the other way. Why is that?
Oh, so I want to clarify that counter rotation isn't about clockwise or anti-clockwise. It's the opposite or the same direction of the plate. So sometimes we would maybe accidentally let the plate rotate clockwise or anti-clockwise. So if the ball was supposed to be counter rotation and we are rotating the plate clockwise, and you will get the result that the ball is rotating anti-clockwise. So this is a plate, we're rotating it like this. And if the ball is supposed to counter rotate, and you'll see the ball going like this direction. So, however, if we rotate the plate like this, the ball will go like this. So it's not.
Oh, so it doesn't matter.
Yeah, so it doesn't matter. It's just the opposite or the same direction.
Then when the rotation speed goes down, did it just actually go the other way? Did it just rotate the other way?
Yeah. So it will go through. So. Okay, so imagine that you say that the velocity goes down, the balls will go from counter rotate to rotate. So as a result of our experiment, it actually goes through the transition, then to the rotation. When the angular velocity goes down, when it's supposed to be rotate, it will go from rotate to transition, then go to counter rotate because the slide of the ball was biggest in the rotate motion, then the transition, then the counter rotate, so it will go through it.
So as you just said that you think that the plate materials matters for the rotations, then do you think also the ball's material matters too?
Yeah. It may also matter.
Is it for the friction or something?
Yeah, I think it has a lot to say about the frictions. Also the coefficient of friction of the ball. You know what?
Can you just explain how the friction will affect the results?
So say it's affecting through the slide of the ball. So, as I said previously, if the container or the ball's friction is bigger, the ball will slide more, slide less. It won't be possible for it to slide as much as this. So it may just remain counter rotation rather than rotation. Like if the friction is very big, then it will just slide straight over.
Then can you imagine like if your container, like your plate, turn faster, do you think it's do you think the ball moves because of your friction and not the ball rotates?
Sorry.
Because just imagine when the plate go faster, and will the ball just it's like the whole picture. And will the ball they're all together, right?
Yeah.
And then when the plate go faster, will it go bounce around to each other, or does it actually?
So it depends on the space between the plates. So if there's spot everywhere, almost everywhere, then the balls won't bounce. So it's actually in the video. I'll show you. And so if there's just a few balls, then I think you can expect it to just bounce them.
No, I mean that. When the plates actually go faster, it's the plates go faster, right? And as you said the balls how many times?
Yeah.
Right? Well, if it actually go faster, would the ball is not actually turning, then it's actually this yeah, bouncing.
No. Bounce. But it will turn. I think it will also turn and also bounce. Yeah, it will bounce because you mean bounce at y-axis or
X-axis.
yeah, it's the bouncing is also a kind of I would say the rotation is also a kind of bouncing.
Then how do you observe velocity?
You mean
Velocity?
the velocity?
Yeah.
Observe the velocity of what?
Of the rotation.
Of
Rotation.
the plate or
Yeah, the plate.
so we use the we put a sticker on the plate, right? So we just use tracker and track the position of the point on the plate, and this is our x and y, and we use some programs on Excel to find the maximum and the minimum of the position, and we do some calculation and find the period and calculate the angular velocity.
Thank you.
Okay. So now we opponent summarize the discussion.
As I just said, I asked the reporter that when the plate actually go faster, will the ball bounces for your x-axis and not your ball is turning. And he said that the reporter said that when the plate actually go faster, it don't bounce to the x-axis and also turn, the ball also turn. They both do that. Because if you think that rotating also describe the bounces. Right. And And also, like, I asked him, like, will the materials of, like, the plate also, like, the ball matters for, like, the rotation? And he said that, yeah, it matters. And it matters for like, the friction of it. And, yeah. I think that's probably it.
Thank you. The question of the reviewer to the reporter and the opponent.
So first, I want to ask both reporter and opponent, do you think that how many forces are there? That which force are there in this system? Let's go first, reporter.
So there's the friction of the balls and also the friction from the plate to the ball.
Friction, just friction force.
Yeah, and also the ball has inertia velocity.
And how about opponents?
I think, like, kind of like same methods, but also, like, I think gravity matters. Like, the weight they have.
Oh, okay, thank you. And so, for the reporter, do you think that if the observer inside or outside the container matters? The observer inside of the container or outside of the container
You mean
matters?
the track of the ball?
Yeah.
So actually we
You check it in like the view outside of
yeah we also track
But-
outside.
But that is inertia system. You change it to like non-inertia system.
Non-inertial.
Yeah, just the observer is
It's
inside.
inside.
Yeah. Just
So
change it.
our tracks are actually all on the where pertaining the observer are on the inside.
Inside.
Yeah, all of our tracks shown on the
Okay, thank you. And do you think that if the observer inside of the container or outside matters? Matters to all the data of or the forces we have to calculate. Do you think that if the observer inside of the container or outside of the container, will that affect the experiment result?
Yeah, I think it will.
Okay. And do you think that which condition that the poles start to rotate in opposite direction? Like how many poles or how many the ratio between the pole surface and the surface of the container? Do you find out the limitation?
Yeah. So there's our chart that we shown here.
Do you think that which is okay?
Okay, can I?
Yeah.
So there's the limitation, like when the velocity is at 30, about 30, the ball will actually turn from counter rotate to tension.
Thank you. Do you think that in which condition, like, do you think which is more important, the amount of the poles or the ratio between the surface of poles and the container? Okay, here's all of the questions.
Thank you. Preparation of the reviewer. 2 minutes. coordinator, the reviewer takes the floor.
Okay. Hello everyone, I'm Corinne from Team ECN 1917, and today I'm going to review to you problem number 15, pancake rotation. We think that it would be, you have to be mainly focused on explaining in which condition 3 points of motion can be observed and investigate how does the parameter affects the frequency and the angular velocity. So overview of the reporter. So first, for the phenomena set up, they got motor, knob, and watch, and counter rotation. And rotation rotate in the same direction and the opposite direction. And for theory, now inertial system coordination, cluster motion, the space, and fill in the ball. And analysis of the counter rotation, regular pattern, the space direction of the balls, motion direction compared to the container, and check the shape of the ball's motion. For experiment, they have 3 parameters, numbers of the rotating balls, angular velocity of plates, diameter of the balls. For conclusion, numbers of balls increase, more likely to have the motion of counter rotate. Okay. So for cross-well phenomena, explain the path, track, shape of the ball's motion, and investigation sticks to a problem statement that the counter rotation of the balls. Nice demonstration on the experiment device, the setup, and yeah. For cons, they didn't clearly define the transition before after rotation, and the space movement direction and the motion direct to the balls didn't be clarified since relative position between observer and objects affects the motion we see. So when it is in non-inertial system, we have to add Coriolis force to explain the system. Okay, so overview of the opponent. Summary the definition of counter reverse rotation. A material of the ball is a kind of parameter. Cons well discussion about the friction and ball's motion and the interaction between the balls. And for cons, lack of discussion of how the formula fit with the experimental data and derivation between. So for the discussion, I want to ask, do you think there will be any other variation affects the result? And reporters say that the material of the balls. We think that since the plate friction is main reason that causes the balls to rotate, perhaps changing the material of the plate will also be an important factor. And I want to ask, what do you think of the bounce of the balls? Reporters say that rotation is a kind of bounce, and we think that it is a kind of energy transform. Yeah. So for missing points for reporter and opponent, the first diagram should be discussed since the centripetal force will be changed to a centrifugal force according to a relative position between the observer and the objects. So as for the relative velocity direction, will also be affected, like counter or clockwise. For reporters, since part of the analysis includes angular velocity, perhaps a relative angular velocity to the container and clockwise positive and counter rotation should be considered. And also, we think that it may be a transition zone that between that some balls, there be a transition zones that some balls will rotate in the same direction, some balls in opposite direction. So maybe they can observe the phenomenon.
Okay. Thank you.
Thank you for it.
So now the concluding remarks of the reporter.
So I'm here for the concluding. So for the opponent, she asked about the units of the axis, and the meaning of the airspace, and also the factors that affect the motion. And also, we explained about how the friction affects in more detail. And so, also the reason why we put the origin in the middle. And for the last two is that the ball, so why does the ball counter rotate in other cases and the ball will bounce? for the reviewer, she asked about the forces that exist in the system, and also the questions about the observer on the inside or outside, and the conditions that the ball will reach, whether counter rotate to transition or transition to rotation limitation.
Thank you. Questions raised by the jury. Okay, Professor Lee.
Few body and many body motion are quite different. You give us a quantity coverage to describe it. It seems like a good idea. And maybe I missed some point during your talk. Do you ever give us the ratio value of the coverage when the many body correcting motion comes in?
Sorry, can you repeat?
Do you have a ratio of critical coverage value?
Strategy of
Yeah.
Critical coverage.
Or ratio coverage about that when the corrective of many body effect comes in.
So, do you mean how do we get the coverage, the value of coverage?
Yeah.
So,
Few low coverage and high coverage are quite different, right? The motion.
oh yeah,
Sure.
So,
I mean, but my problem is whether there is a sharp value or to distinguish to those two types.
okay, so
Or whether there exists such a sharp value.
there's, I would say it's a continual process. It is not an like sharp limitation. So actually, like we're kind of not really confident about setting the limits here, because actually the counter rotate to a transition is when the slide of the ball gets bigger. So we're like kind of using our judgments to judge how what is counter rotate and transition. So also we found out that in short coverage, the balls intend to just rotate rather than counter rotate.
Your opinion?
I guess it's kind of something like what Rupert says.
We think that with too many balls, maybe it won't just rotate in the other direction. It will just like stall right there because there's no that much space for it to rotate.
Would you turn to page 23? As the angular velocity of the plate slows down, you'll see the transition from rotation to counter rotation.
Yeah.
And could you explain again why you see this transition? What's the physics behind this transition?
Okay, so if the angular velocity is bigger, then the balls will also have the bigger rotation speed. So the slide of it will be bigger. So it will be intent to rotate rather than counter rotate. So if the velocity is lower, the ball won't slide that much as the condition is bigger velocity.
Yeah, you described the phenomenon.
Oh, yeah, I described it.
I'm asking why.
So I think it's so the frictions are basically the same in these conditions. However, when the ball's velocities are bigger, it won't get to zero velocity with when it's sliding, its velocity is bigger when the angular velocity is bigger. So when it won't the speed won't decrease to zero that fast, so it will slide more.
Same question for
Sure.
the reviewer.
Blackboard. Yeah. So the thing that affects the rotating motion would be the angular velocity of it. So here would be the angular velocity, and here would be the amount of force, or we can say that it's the surface of the pole, like the amount of the pole. So right here, it will be clockwise, and here will be the transition zone. That is, some of them are clockwise, some of them are in the other direction. And here will be the reverse, and here will be the stall. Since that it is like too many poles, it won't have that much space to rotate, so it will just remain at stall right there.
Great. Opponent. Let's opponent. Do you want to say something about it?
Yeah, like, I think it's also about like the force and the angle of earth.
Okay, thank you. Please have a seat. So now jury make a rating. Rating. Okay, the score for the reporter. 6, 6, 6, 5, 6. Okay. The score for the opponent. 6, 6, 5, 5, 7. Okay. The score for the reviewer. 6, 8, 7, 7, 7. Okay, thank you very much. So we close our second stage and take a 10-minute break. Thank you.
And we would like to show them problem number 4, color line. Where's that?
Oh, okay, the problem number 4, okay, color line. Okay, so each team please write down the representative name on the blackboard and the preparation of the reporter. 5 minutes. Okay, the reporter will give a presentation.
So hello everyone, my name is from Team, and I'm from Team 81, and my topic today is color. So this is our table of contents. We have the problem statement, observation, problem investigation, experimental design, experiment results, and the conclusion. So our problem statement is when a compact disc or DVD is illuminated with light coming from a filament lamp in such a way that only rays with great angles of incidence are selected, a clear green line can be observed. The color varies upon slightly changing the angle of the disc. Explain and investigate this phenomenon. And our main discussion is to discuss the principle of color appearance on the disc and the relationship between incident angle of light and appearing colors. This is our preliminary observation. And the first picture features a disc under multiple light sources, and the second one is with a single light source. And this is our observation video. So our problem investigation is we first want to investigate the formation principle of color on the CT. So the tracks of a disc act as a diffraction gradient and producing a separation of the colors of white light. And it is a direct evidence of the wave character of light, and it has a sharper pattern than a double slit. So first I'm going to talk about single slit. And so in this picture, we assume a wave coming from point source S and passes through aperture D and is diffracted. And with the primary incident light beam landing at point P and first secondary maxima occurring at point Q. So when the wavelength exceeds the size of the aperture, we experience diffraction of light according to the equation sin theta equals lambda divided by P. And the next picture is the diffracted light intensity distribution, and we can get the formula on the left. And the A stands for the amplitude of the incident wave, and the R stands for the distance between D and Q. And the function of X is the inclination factor. So this is the diffraction of double slit. And as you can see in the picture, we can get the formula on the left. So the R1 and R2 are the distances from the slits to the first order frame. And lambda is the wavelength, and n is a constant. Finally, there's our diffraction gradient. So each ray travels a distance, d sinus theta, different from that of its neighbor. And we get the formula d sinus theta equals n lambda. And the d is the distance between slits in the gradient, and the lambda is the wavelength. And m is the order of the maximum. So the slits are usually closer in diffraction gradients than in double slits, producing fewer maxima at larger angles. So next is our experiment. This is our experiment 1 setup. You can see in the picture we have a stand with a flashlight and a disc on the table. This is our measurements of experiment 1. So we use the idea of the angle of incidence equals the angle of reflection, and we change the viewing angle of the observer and observe the colors that appear on the disc at different angles. Our process is first we shine a light with a single source on the disc from a distance, and we use the camera function of the mobile phone to find the angle at which each color appears. And we side view when looking for angles at different colors. And then we use the program to analyze the angle of the mobile phone shooting a sequence. So we try to find a color with camera function, like the picture, and we use image J to analyze the angle. How we define colors in experiment 1 is that we use the program Procreate to find the code of each color. And we match it with a form with many color codes, and we see what the color is. This is our experiment 2 setup. And we have a white line vertically incident on the optical disc, and the rear panel helps to interpret the range of each color. This is our measurements in experiment 2. The process is we draw scales on the board to see color spread range, and we shine a light with a single source on the disc from 31 centimeters away. And we take photos to record the distribution range of rainbow colors produced by light due to diffraction. And this is our first result. As you can see in the picture, number 1 is when red appeared, and number 2 is when yellow and orange appeared, and number 3 is when green appeared, and 4 is cyan blue, 5 is indigo, and 6 is purple, and 7 is when purple vanished. So the angle of this incidence is like the opposite of the next chart. The appearing range of colors is that we use the data from the last experiment to analyze the data. So we find that after an irradiance routine, a combination of red, orange, yellow, and green line appears. For experiment 1, we found out that as the incident angle of light increases, starting from red, yellow, orange, and green, cyan, indigo, purple appears sequentially on the disc. And finally, there is a combination of red, yellow, and green. And the red's appearing range is the biggest of all. So, experiment 2, we have a white light being diffracted by an optical disc, and the red light has the largest range of all, and it matches the result of experiment 1. So from the near center to the periphery, in order purple, indigo, blue, green, yellow, orange, and red appears. The explanation is that the light is diffracted in a pattern similar to a double slit, with bright regions at various angles. And the central maximum is white, and the higher order maxima disperse white light into a rainbow of colors. Our conclusions are, when a light hits a disc from a distance, the color on the disc varies upon slightly changing the angle of the disc due to diffraction gradient. And with a single light source, which is white light, the color on the disc appear in the order red, yellow, orange, green, cyan blue, indigo, and purple. So red appears the most. And when a light is diffracted by the disc, the pattern shows from near the center to the periphery are purple, indigo, blue, green, yellow, orange, and red. And finally, the experiment 2 agrees with the results of experiment 1. Oh, thanks for
Thank you. Now the question of the opponent to the reporter.
And how did you define the green that is thick? How did you know that it is green? Have you do any analysis for it or?
Oh, yes, we use the program.
Oh, right. And where do you have picture of it? Is it parallel to a light source, or in which or it depends on where do you view angle?
Oh, so I picture it when I see the color.
And so in your observe, the green is all the line is instead of the shape. Oh, it is like a line. It's not a shape.
Yes.
And does the green line only appear in the large incident angle?
I believe if we look, because I think there's a routine that's going on. So.
Okay. And have you researched on the power of the light?
Power? Oh,
yes.
no.
And do you find that the different viewing angle in the line may be not strict?
You mean not the same? Like, I didn't choose the exact precision to take the picture, but all my results, the data are kind of similar. So.
Oh, and do you analyze the and have you ever observed the other? So you have observed other color in the line, like for red to purple. All of it can be observed.
Yeah.
So your parameter only change the view angle.
Yeah.
And the problem statement said that we have to observe a green line. So do you think you observe for red line to the purple line is important to your experiment?
I just want to see the.
Sorry, so we have to move to the one preparation of the opponent. Okay, the opponent will take the floor.
And hello everyone, I'm Typt from Team E10 1917. And today I'm going to opposing problem number 4, color line. And for problem statement said that we have to since the difference lies in certain angle, and we can see a clear green line. So we have to explain this phenomenon. So our main focus is why the color green line can only be seen in a large incident angle, and why we can see a line instead of a shape. An overview of reports for their phenomena. They have shown that the green line they have shown that a single light source and multiple light source, and actually for a single light source, and it will be a line in a bit. But for a multiple light source, it may be many colors of light, and the formation principle of CD light. And theory part, they use diffraction gradient. That's because the CD is combined many peaks, and they have diffraction single slit and diffraction double slit. And they also use Young's equation. They also use Young's double slit. And for experiment, they have changed the view angle. And for conclusion, and the light is diffraction in a pattern angle, so I see different things of color. And for the red color, it will appear the most. And they also get a conclusion about since the viewing angle becomes bigger, and the color they think will be start from the red to purple. And some advantage and suggestion. They will showing the process of they will showing the experimental process, and they show the observation in the experiment, and they use a different fleeting angle, and observe will have a different kinds of angle. And we will describe what they do in the experiment. And also, for suggestion. And actually, I think that they don't explain what caused this phenomenon in detail for why we can see a line, why we can see a green. And they didn't stick to a problem statement. For the problem statement said we have to observe a green line. And but I think that they discuss about red to purple, and it's a good idea. But I think that they can explain their experimental results with their diffraction gradient formula. And actually, they can use diffraction gradient formula to calculate what is theoretical value to fit with their experiment. And yes, so I think I will discuss about the reason for why we can see a green line in the large incident angle, and also why we can see a line instead of a shape for multiple incident angle, multiple incident line, and a single incident line. And for the interference, and also diffraction gradient. Diffraction gradient they use to explain this phenomena, but they didn't stick to their experiment. And for the experiment, I would like to discuss why they use a different view angle, and they will have a different color they see. And also for Young's two-slit equation. And let's move on to the discussion part.
Now the discussion.
Could you explain that why do you use Young's two-slit equation? Young's two-slit interference. Yes. For your could you turn to this page here? Thank you. Because we know that Young's two-slit, yes, it only can be used with two slits, but do you know that CD has many slits? Yes. So what do you think this can be used?
Oh, because I thought that it is quite similar to the diffraction gradient, but the pattern will be like less sharp. Like comparing to double slit.
So you think the Young's two-slit interference only can is only your tool to explain what is diffraction gradient?
Yeah, I do think that. Yeah.
And I'm going to discuss that here. And actually for your diffraction gradient, and you have drawn a picture like this, but for your formula, you write like this. And you write your formula in here. Diffraction gradient. Yes.
what is theta? Theta means the incident angle or your view angle. Incident angle. And so this formula is defined in the website, right? Yeah. Okay. And so what you see in the theta is incident angle. For diffraction rate, actually we got the incident angle, and then we got the diffraction angle. So what can we consider about? Maybe your formula need to find theta I and theta s. And I think maybe it should be right like this. And it is because you when you do an experiment you have a test difference. So test difference. You know what? And so for your incident, so you know what's the angle of your incident light, right? Yeah. So have you calculated what's the no? And for the view angle, actually you have many view angles. You have many view angles. And here, the C, you know what it is? What? The distance. Yes. The distance between the two sticks. And for lambda, and do you know what M? Yeah, like intensity. Oh, and actually you can calculate what's the lambda, and because you already know this one and this one, so you can calculate what's the lambda of your. You can calculate what's the lambda that you can see. And could you turn to your experimental results for in different view angle you have different light. And the x-axis is view angle. And the y-axis is red. And I think maybe you can try to rewrite here is red and purple and find what lambda is and which lambda is bigger. You have any idea? Yes. Which one is bigger? No. What's lambda? So it's bigger and the lambda is smaller. So maybe you can try to use this formula that you can put in your experimental data and you can find what's the lambda is. And when you find what's the lambda is, and you can know if it is more bigger and the color of it will reach to a red. And if it is smaller, the color of it will be purple. So maybe you can use this to explain why your experimental result will like this. And for this part, I think maybe after you do analysis this and you will find this result. And what's the reason that we can see a line instead of a shape? I think it's like this. It has a certain way to because of a shape. I also think it's because of shape. And can you interpret with your say that why we can see a light is related to phase, right? And we already talked about the diffraction. So when you only use your light source, it's like a light. So it's only one light. When it's only one light, and then in a diffraction, so how many incidents like you think you have diffraction light? So maybe for example, here is your CD, and you have here is a pit, okay, pit and it, and when you have a line incident into it, and what's the refraction line? So maybe you will cause because it acts on different pits, so it will cause different. It will cause a different refraction line. So when you combine all the refraction line together, then you will get like this one. So here the intensity is the biggest one. Like the diagram shows. So maybe a CD, and you only can observe here is have a line. So here, if you can see like this, and the intensity is very small. So it's very small, so we can't see it only by our eye. So that's the reason why we can see only a line on the disk. And and do you think that it have a limit for diffraction for the incident angle? Yes. Does it have a limit? So what's the limit? 90 degrees. Oh yeah, it's 90 degrees. So maybe you can rewrite the sentence like you have write that maybe this side theta m equal to n9. And here the sine theta m you say the limit is 90 degrees. So when it is 90 degrees, that means it may be smaller than sine theta. Sine 90 degrees is sine 90 degrees is 1. So it may be smaller than 1. So we can rewrite a function like sine theta m should be smaller than 1. And we can rewrite a function, and you can try to rewrite it. We can for example put an m here and b and lambda here. You mean like divided? Yeah. So here is only m, and here the b is divided. Yeah. So it means the lambda divided by d divided by lambda should be bigger than the m. So m have a limit. Yeah.
Sorry, the opponents summarized the discussion.
For discussion part, we have discussed about Young's two-state equation, and we think that the CD has multiple states, but Young's two-state equation only can use for 2 states, so it perhaps to be revised. And for incident angle, the angle should be defined more clearly, and about diffraction angle and the incident angle. And because in the experiment have shown the different incident angle will cause a different result, and we also use the diffraction gradient formula to explain the reason for they can calculate the theoretical value of what's the wavelength. And when we know what's the wavelength, we can know what's the color of the light. And for diffraction single sight, and diagram of the amplitude cannot explain why the color can be seen, and perhaps the reporter can verify it. And we also discussed about the intensity, and intensity will cause why we can see the light.
Okay, thank you. Now the questions of the reviewer, the reporter, and the opponent. Reviewer, please.
Okay, so the first question I'd like to ask is about white balance. When you take photos on different cameras, the images actually look different. The photo taken on one camera may look more yellowish than the other. So, do you consider that, and do you think that's important?
Yeah, I think it does.
And how do you think we can control it?
By using like one camera.
So you can same camera. Okay. And what do you think about this problem?
Can you explain again?
So the problem we're talking about is white balance. Photos taken on different cameras can be different. The colors can be different. And how do you control this?
Control. You mean control the view angle of the camera?
The color of the camera.
Oh, you mean the camera.
Yes, there's difference between two cameras.
The distance between two cameras.
So there is difference in the image.
Oh, and we can control ISO aperture.
Excellent. Okay, so let's think the setting. Okay, so the second problem, can you please switch to the problem statement? Yeah, so the images on the problem statement, it actually has two lines, right? It have three, or yeah, it's a two. So what do you think is the cause of the two lines?
I think there are two light sources.
Two light sources. Okay, and do you agree? Do you agree? What is the cause of there's two lines?
And maybe it's because of the curve.
The curve of
and maybe it's the page on the disk. Maybe it's not irregular or what.
So you only think there's only one light source?
Maybe you have one light source will cause only one light. But if their incident maybe their incident light they will become more one light will have a two maybe they have two light source or they are not parallel.
Oh,
so you have a two
light sources. Okay. The third question is how is the angle of the camera measured? I think we saw you use trackers to find the angle.
Yeah.
And do you think that's good, or is there better than this?
Oh, I don't think that sometimes it's not like too accurate to use that, but I have to find the parallel. Like the phone has to be parallel with the direction I shoot the color on TV.
And I think for camera angle, and we can measure distance between the disk and the camera, and then we calculate what's the height of the camera, and we only need to use arctangent to calculate what's the angle of it.
Sorry. So now we move to the next phase, preparation of the reviewer. the reviewer will take the floor.
Okay, so hello, I'm the reviewer of Team Trivial, and now we are reviewing the problem 4, color design. So the problem statement is shown in the report, and our key point is the vector's type, respective angle, and the correct angle measurement methods. Here's our overview. So an overview of the report for the phenomenon, the reporter gave us preliminary observations and sharp patterns. For the theory, they focus on single and double slit diffraction. And for the experiments, they told us how they analyze colors and angles. The conclusion, they gave us that red color appears the most, the angle affects the color, etc. So comments of the report. The presentation is neat and clear, and they also have error bars. What's more, they have clear graph. But there's some suggestions that we would like to give. First, they should explain how each experiment is different. Because there are 2 experiments. I don't think they explain well how they are different. And they should define the colors more rigidly. Also, they should consider the mechanism of the diffraction on the disk and not focusing on the slit diffraction mechanism or theory. And also, they lack more experiment data. Also, they could improve on time management because they have 2 minutes left. And on page 11, we can see that the environment is not well controlled because the curtains are actually open. We can come back to that in a minute. And as the opponent says, the problem statement is not strictly followed, which is said by the opponent. And for the opponent, in the 2-minute section, they asked many problems. And in the quick report of 4 minutes, they also did a very good job. But there's many questions in, the quick report is 4 minutes. And time is not properly spent in the 10-minute section, which we will discuss. So for the discussion, how screen defined, the reporter says the program is used, and we think that a clear RGB value should be given by the reporter. So where's the angle view? The reporter says it's given the sign. And we think that for every experiment, the opponent should give a numerical value for the angle. So the opponent asks, why can the Young's diffraction theory be used? The reporter says the diffraction is sharp, which is similar to that of double slit diffraction. We think that the opponent is right, and the reporter should investigate more on the mechanism of the diffraction and not just plainly on the theory. So the next question, the formula should be related to both the incident angle and the reflection angle, and we agree that it should be adjusted. So is there a limit? Yes, the limit is 90 degrees. So my question is that about white balance, and the reporter says we should use the same camera to control that. The opponent said we should set ISO value, and we agree with both. So there are 2 lines in the problem statement. So the reporter says there might be 2 light sources. The opponent says there may be a regular flaw on the disk. So we think the image should be more considered. Also, there should be better method of measuring the angle and not using tracker. So some missed points. The biggest missed point is that the opponent shouldn't be talking about theory in the 10-minute section. Instead, it should focus on the experiment. Also, the relationship of double slit refraction to the diffraction of the disk should be first discussed, because I don't think they discussed it. And the opponent should also be focusing on the mechanism structure of the CV and not just on the theory. And for conclusion, there should be more discussion about the other parts than theory in a 10-minute discussion. And that is my review.
Okay, thank you. The concluding remarks by the reporter.
So my concluding remarks are that the opponent asked me that how did I define the color, and he asked me if observing the red light to the purple light important, and then she asked me, have you ever observed other lights, and is all colors aligned, and do you think the angle have a limit, and what is it, and how can you control the angle of the camera? And she talked to me about the formulas on the blackboard, and which I can get I can get the lambda sorted out. And the reviewer told me that asked me that how I control the camera, the pictures, colors, and like in our problem statement there are two pictures, like they have two colored lines, and they ask me why. And they also asked me about the angle of my from shooting a CD. Yeah.
Thank you very much. Now the questions from the jury. Professor Mann.
You turn to the problem statement. Maybe the second page. I think your opponent has pointed out that this problem was to observe a slight changing of the angle when you see a clear green line, right?
Yeah.
But I didn't see it. Did you do it?
You mean a clear green line?
When you see the clear green line, then you tip your disc and you can see the variation of the color.
Oh,
Did you do that?
I did. I did.
Okay.
Any questions from the jury? Okay,
But
Professor Lee.
we saw the rainbow's color. We think about the refraction, not the diffraction. So I thought to you, your observation is about the reflection phenomena, not the diffraction phenomena. Rainbow's color is caused by the reflection of the light, right?
Yes.
So you analyze your experiment by saying that it is caused by the diffraction, but I cannot join those two.
I mean, like we did like use the white light to like illuminate it on the CD, so we see a rainbow of color. So I think that is
Maybe you cannot see the appearance of the green light because you did not check the diffraction phenomenon, just check the reflection. As Professor was asking. Right?
Yes, so I think the refraction and diffraction should be both checked.
And I think the reflection is it also is a main reason for this problem. And yes.
Any questions? So I have a question to the reporter. Could you go to the page 2020, the experimental one result? Okay. I noticed that the first data point was taken by the incident angle of 90 degrees. How do you do experiment with the incident angle 90 degrees? So this is your white light source, and this is disk. So 90 degrees. This.
no, I didn't change the angle of the light. I said.
Angle of the incident color.
No, I changed the viewing angle.
Viewing angle. Viewing angle. So here the vertical axis is the viewing angle.
It's like I use 90 degrees to minus the viewing angle, and I thought it was the incident.
Okay.
I think
I'm not clear.
I think reporter's opinion is about the viewing angle equal to an incident angle because of diffraction.
Viewing. Thank you. So I also have a question to the reviewer. You point out there are two green lines on the disk. What do you think about this phenomenon?
I agree more with the opponent. I think the shape on the disk is not just a simple double slit. So there may be a curved structure, and that might be a cause of
The two green lines on the disk.
Sorry, may I clarify my
Sure.
response for this, Professor? Okay. And I think the reason for why we can see a rainbow is because of diffraction grating it can separate the light, so we can see a rainbow color. Thank you.
Thank you. So now the jury make the grading. Jury are ready? Okay. The grade for the reporter 5, 5, 5, 5, 6. The grade for the opponent 7, 6, 7, 7, 7. Okay. And the grade for the reviewer 7, 7, 5, 6, 7. Okay, thank you very much. We will close the this 6